Alright, hello. We are going to finish our discussion of Section 2 for Chapter 9, moving on from just conservation of momentum with one-dimension collisions, and now we're going to look at two-dimensional collisions. And so remember that momentum and impulse are vectors, and so we can break them apart into their components just like we could with force. Alright, so let's take a look at an example. So we have two billiard balls, and the cue ball strikes a stationary object D. So we have... Where's my pen? I can't find it. There it is. Okay, so we have some ball D, and then we have the cue ball, and initially it's moving with a momentum, and object D is stationary. And then they're going to collide, and we're going to see what's going to happen. So for the momentum of object C, we have the initial momentum of object C, and the momentum of D is going to be 0 since it's at rest. So if we look at the momentum of the system before the collision, it's basically just equal to the momentum of object C initial, so whatever its mass and its initial velocity are, because it's the only object in motion. So since we know that initial momentum equals final momentum based on the law of conservation of momentum, we know that all the initial momentums, which really are just object C, since object D is not moving initially, that's going to equal the final momentum, and since object C is going to hit object D, they're both going to be moving after the collision, and so we have momentum of both objects final. Alright, well when these objects collide, they're going to collide at an angle. So initially we have object D and object C, and it's going to hit it, but what if it hits it at a bit of an angle? So then afterwards, let's say we're going to have object D go off in this direction, and object C is going to go off in this direction. And so now we need to calculate the final momentum of each object, but they're at angles. Well, momentum is still conserved even for components of vectors. And so we're going to assume that the x-axis is the direction of initial momentum. That just makes things easier. It's kind of like when we had free body diagrams and we had things at angles, we turned it so that it was sitting flat, and that just makes things a little more simple. So if we say that the x-axis is the direction of initial momentum, then the y component of that is going to be 0. And so if we look at afterwards, so initial, before the collision, we only have motion in the x direction, and so we'd say y initial is going to be 0. Now afterwards, we've got this hypotenuse of momentum for each object, and that means that we've got an x and a y component. So if this is our D, this is momentum final for D in the y direction, and this will be momentum final for D in the x direction, and we could do the same thing for object C. Now, because our initial momentum in the y direction was 0, that means that these y components for the momentum of object D and the y for the momentum of object C are going to be equal in magnitude but opposite in direction because they have to cancel out to 0. So now let's look at the x direction. So for the x components, we know that initially the object was traveling in the x direction, and so we can get our momentum of object C initial in the x, which is the only momentum component, and then that is equal to the momentum of both objects in their x direction, since they're both also traveling in the x direction after the collision. And so we'll need to find the x component of that. Well, we can also conserve angular momentum. And so the law of conservation of angular momentum says that if there are no if no net external torque acts on the object, then its angular momentum won't change. So we could say that the angular momentum initial is equal to the angular momentum final, remembering that we use capital L to denote angular momentum. So if we think about a spinning skater, its momentum, his or her momentum, is conserved. If they want to spin faster, they pull in their arms and they decrease the radius from the center or the axis of rotation. So to conserve momentum, we must decrease the moment of inertia, which means to decrease that radius of rotation. And so that's what happens when you pull your arms in. You're decreasing that radius. If you extend your arms, you're increasing that radius. Okay, so we're going to do some practice problems with this because this does involve breaking things up into components. But you're more than welcome to take a look at them ahead of time. And then once we've completed the practice problems, here are some that you can do on your own along with all the answers. Have a good day.